Right. So we're back. We discussed about the normal distribution last time. So our topic today, I'll be talking about the uniform distribution. In fact, I am sure that you remember that we did something related to uniform distribution in the middle of the previous lecture. And you might recall that we did something about that uniform probability of observing something and uniform the equation b minus a over 1, sorry, 1 over b minus a. We talked about that equation. So just to have a little bit of a momentum going, what is the idea of uniform? What do you mean by uniform? Uniform. Can somebody tell me what is the meaning of uniform? You can put it into the chat if you can't speak out. I'm looking at your chat. What is the meaning of uniform? What do you mean by uniform? The word uniform. Yes, so one answer is you look like. Good. Look alike. Very good. So any other? If you have any singular word also, you can share that with me. No issues, but put it in the chat. Okay. So what do you mean by uniform? So one idea is look alike. Any other? I'm observing the chat. Similar. Okay, very good. Right. There's another word. Similar. Any other? Look alike. Similar. Constant. Okay. Okay. Good. We'll talk about this. Constant. Constant. Unchanging or constant. So I'll keep constant and also unchanging, I guess. Unchanging. So we have two words there. Right. Invariable. Okay. Very good. Invariable. In invariable and same form. Same form. Equal. Right. Okay. Very good. So steady. Right. Okay. So there's another word called steady. Right. Okay, thank you. Right, now let's look at these words. Now, when we think about the idea of the word uniform, certainly all these words would come into your mind, right? So uniform, let's think about uniform in the context. So if you have thought of this, let's say you have a school and right, you have a school and then you are asked to wear a certain uniform, right? So you are asked to wear a certain uniform. So it should be like this, and there is certain length and then also the size of the shoes and everything. So you are asked to wear a uniform. Girls and boys. I can't draw girls. Let's say the girls. Right. So uh, and if you have certain uniform, Actually, the word uniform means all these things equal, but I'll skip using the word the idea constant here, because constant in mathematics means something that is constant, where a variable can have a constant value. So constant means something like this. But yes, uniform function, the uniform probability distribution is a constant function. We'll talk about that. And unchanging is also true. It's unchanging in the sense it doesn't change because it is uniform. So look-alike, invariable, it doesn't change. Steady, yes, the uniform function is a steady function because it goes parallel to the x-axis. So you can call it that way as well. And equal, same form, similar. So all these things, all these concepts have a place when you think about uniform. So in mathematical terms, the uniform distribution, if I write it, in terms of a uniform distribution as a definition sort of a, so a uniform distribution, it means a value has the same probability of occurrence everywhere or anywhere in the range between the smallest value and the largest value. So in the case of a uniform distribution, a value, a value has the same probability, has the same probability of occurrence, right? Same probability of occurrence anywhere in the range between the smallest value, let's call it A, and the largest value, let's call it B, right? So because of this uniformity, the nature of having the same probability, you will find the if you draw the function, if you draw the probability distribution, you will find something like this. So you have if you draw the probability distribution here, you will find that the curve would look like something like this. It's a line. It will be just a line like this. And of course, it should not start at the zero itself. There is a smaller value as well as a larger value. So if I write, this is the smallest and this is the largest, B, right? So this is how a uniform distribution would look like. You have your probability, that is the fx, and the random variable x here. So random variable x, if you think about it, the random variable x ranges in A to B and A to B or B to A, whatever, and the probability fx is equal to 1 over B minus A. Right. Why does this happen? Because when you think about the probability, the whole probability, which is equal to the area under the curve. So if you think about the total probability theorem, the total probability should be 1. Therefore, the area under the curve should be 1. Now, because of that, if you take this thing, the area under the curve, if you take the area under the curve is A should be 1, and that is equal to area under the curve, let's say A should be 1. Now 1, if you think about the height of this one, this height, let's say this is h. H times b minus a, which is the length of this one, should be equal to 1 because the area under the curve should be 1. And this gives us h should be 1 over b minus a. So in fact, h is the fx here. Therefore, I just draw, instead of h, I'll call it fx, and I'll call this one fx as well. And this one fx as well. So that is how this fx becomes 1 over b minus a. Right. Okay, so a is the minimum value, as you can see here in the graph itself. A is the minimum value and b is the maximum value of x. Okay, so some important things to remember: a is the minimum value and b is the maximum value. Important notes, important things to remember. A is the minimum value of x, b is the maximum value of fx. Right. And then you have the mean of the distribution. Now, any distribution has a mean, right? So the mean of the distribution, mean of the distribution, mean of the distribution, mu is equal to a plus b over 2, because it's it's actually the mean and median, they overlap here right at the center. So a plus b divided by 2 is actually the center point. Mu is the center point, mean of the distribution. And the variance and the standard deviation would look like sigma square, that is the variance, that is equal to b minus a square over 12. And sigma is the standard deviation, that is the square root of this one, right? So you can write directly b minus a square divided by 12 square. Okay. So one of the most common uses of the uniform distribution is in the case of selecting random numbers. Right. If you think about in the future, maybe there are things called Monte Carlo simulations and also random number simulations, etc. So one of the most common use of one of the common uses of uniform distributions is using this distribution to sample values, because each value in this distribution has a similar probability, like those words that you mentioned, similar, an equal probability of being chosen. So because of that, when you pick a value, every value in this distribution has an equal probability of being chosen. So that is why I showed you last time. If you take a look at the mean, that say that if we did 1, 2, 3, 4, 5, 6, if you remember those set of value numbers, and say for example, I'll take back that example. If you take a set of example, if you take a set of numbers, let's take a set of numbers. So if you take this set S to be 1, 5, 7, 12, 20, 30 sort of. Now, if you take look at this set of numbers, you can see that each of this number has a single probability, like it's the same probability because you have 1 only once here, 5 only once, 7 only once, 12 only once, 20 only once, 30 only once. So the probability of choosing any number is equal to what? 1, 2, 3, 4, 5, 6, 1 over 6. Because it's just one number out of 6. So because of that, when you have a set of numbers like this, the probability of choosing any number is the same. So this is a uniform distribution. But it's actually a discrete uniform distribution because you have discrete numbers. In the case of continuous uniform distributions, throughout the range, starting from A to B, you have same probability of observing a value. So that means if you take look at something that is like a length, for example, if you take the measurement of a, say you take a piece of ribbon. Okay, so you have a ribbon. Now, if you take, let's assume that the ribbon looks like this, a square, a rectangle thing. So this is a ribbon. It's a ribbon. So when you think about a length between, so you start with 0, this case, and the length of the ribbon, say 5 centimeters. So the probability of cutting any length between 0 to 5 has the same probability for a given ribbon, right? Because if you say, I'm going to cut from here, so let's say that I'm going to take this ribbon. So I'm going to take the ribbon and I'm going to cut it from here. Say I'm going to cut it from this place at 2.3 centimeters. So if I'm going to cut it from here, you have the same probability of cutting it from somewhere here, maybe 4.7 centimeters, because that's just one ribbon, and you can cut it from the first for the first cut. For the first cut, you have an equal probability for any length because you have the 0 to 5 length, right? So similarly, that's what it says. If you have, like, if you think about many 0 to 5 centimeter ribbons, then you can cut in any length and you can have a uniform distribution like this. It's a uniform distribution with the length that you want. You can have equal probability for all the cases, right? So that's about the uniform distribution, and let's do a calculation. I think I have something here, right? Let's start with the very simple first calculation in this book. So you have your textbook with you. You can refer to that when you have if you have it with you. So let's look at this first question. I'm going to take the question, maybe I can take it. I don't know if I can take it like that. Uh, so this illustrates the uniform distribution with A0, and okay, I can, yeah, rather than taking it, I can annotate it. So I'll annotate here, and you can observe that. Right. Now the question says, figure 6.3 illustrates illustrates the uniform distribution with a so figure 6.3 illustrates a uniform distribution with A equals 0, B equals 1. So here A is equal to 0 and B is equal to 1. The total area inside the rectangle is equal to the base 1.0 times the height. So as I told you, the base is 1 and the the height is 1 and the base is 1. So think about this, the rectangle generated from this one, 1 times 1. So the area under the curve is 1. Thus the resulting area is 1. Satisfies the requirement that the area under any probability density function equals 1. So in this uniform distribution, what is the probability of getting a random number, between 0.1 and 0.3? As I told you, the first thing that I told you about the continuous distributions is that the continuous distributions do not have an equal value. Remember, when you think about the normal distribution last time, I told you, you don't have an exact value, a probability for an exact value, because the probability is defined as an area under the curve. So in order to make an area, you should have a 2D strip, right? So if you just have a single value, you don't have a probability for that exact value, because you can't do the the simple terms is that you can't do the integration, but the real thing is that because the value is continuous, you can't actually expect a probability at a value that reaches 0, because there is no the density itself doesn't add up to a probability. So all in all, the idea is that you can't have a probability value for a given thing. The example that I wrote earlier, it's about the discrete values, so single values. You can pick single values, and I told you that the probability is the same for that set. So that's a discrete distribution. But when it comes to continuous distribution, uniform continuous distribution, you can't have a value, an equal value, and have the probability for that. You should have a range. Okay, so a random number between the question asks us what is the probability of getting a random number between 0.1 and 0.3. So it's kind of if you take this strip here, this uniform distribution, the problem asks us what is the probability that you have a number between 0.1 and 0.3 right here. So what is this probability of taking a value, a random number? You pick a number, and what is the probability that getting a random number between these two? The area between these 0.1 and 0.3 depicted in this one equal to the base, which is times the height. So basically, it's like imagine you have a pizza, right? So you have a pizza or a cake. So let's talk about a cake. So a circular cake, and you are going to cut this cake. If you cut the cake in half, right, what is the portion that you are going to get? You are going to get a portion of this half divided from the total. So this is actually half, right? So if you cut the cake somewhere here like this, maybe 1/6 or something, then this is the piece, this is the area, and you have the total area. So the probability is 1/6 maybe. Right. Similarly, the range is given as this 0.1 to 0.3 region. So this region. right? The area under the curve will give you the probability, the portion of the whole area. So the portion here is 0.1 to 0.3, that is base times height. The area is basically 0.3 minus 0.1, that's the distance, times the height will give you 0.2. So that's the answer for that area. So if you can find the area under the curve, as I told you earlier, with respect to the uniform distributions, you get the probability. Now, next thing, the mean and standard deviation. So if you look at the mean and the standard deviation of the uniform distribution for A0 and B1, you can remember that the mean is simply the center point. So the maximum plus minimum divided by 2. So very simple. A is 0 and B is 1, so you get 0.5. And variance, you have to remember this part a bit, B minus A square divided by 12. So 12 comes from the equation. You can prove how it comes, but in order to find, remember this one, you don't need that proof. You can actually look at that in the future. So B minus A square over 12 will give you the sigma square, which is this is the variance, and variance is 0.833, and the square root of that will give you the standard deviation. So that's a very simple calculation. It's merely just to get the idea of what is mean and what is variance, and from there you can actually get those values. Let's look at the right. Let's look at some questions. So let's look at some questions here. Suppose you select, right. Let's do some question here, learning the basics. So suppose you select, I'm going to take this. Right. I'm going to increase the size. Right. I hope you can see this the question. Suppose you select a value from a uniform distribution. So when you get a question like this, first of all, better if you can take the idea and understand that it's a uniform distribution, right? The question itself says it's a uniform distribution. Suppose you select one value from a uniform distribution with A equals 0 and B equals 10. What is the probability that the value will be between 5, 7, between 2, 3, what is the mean, blah, blah, blah. So it's very simple. First thing, draw it. As I told you, with in the case of normal distributions, just draw the thing so that you are aware of what to do. And then please do not let me repeat this one again. In the exams, don't write in red color. You can use two colors, maybe um, uh, blue and black, but don't write or draw things in red color. So that's the first and the final time that I tell you, when you are answering, don't write it in red color. So when you want to have this, you can maybe use your pencil or something. You can draw this uniform distribution. You can draw that like that, and then you have 0 and B is equal to 10. So I told you how to find fx. It's easy. You can remember the equation, or you can remember how we did it. The area under the curve, so fx is simply basically 1 over b minus a, so that's 1 over 10. So the uniform probability is 1 over 10. Right, that's all done. Nothing to worry. The probability that the value will be between 5 and 10, 5 and 7. So the question number A, between 5. So you have 5 here, 5 and 7 here. So what's the probability that the value will be between 5 and 7? So the probability or you can write it like this rather than writing the whole thing. P, where x is between 5 and 7, is equal to area under the curve 7 minus 5 times the height. So height is 1 over 10. Remember, the height is 1 over 10. That is how you find it. That is 1 over 10. That's the area. So the total so what is the answer? You can put it into the chat. What is the answer? 1 over 5. In other words, simply 7 minus 5, that's 2. So it's just 0.2. Right. So that's it. Very simple. And also the question asks us between 2 and 3. So B, probability of 2 and 3, I can simply say 3 minus 2 times 1 over 10. So that's going to be 0.1. Right. So why did I choose it that way? The probability times the range, because if you take a look at the whole range, 10 minus 0 times 1 over 10, that's going to be 1. The whole area will be 1, right? So area under the curve. What is the mean? C. What is the mean? Mean is A plus B over 2. So A is 0, B is 0 plus 10 over 2. So that's 5. And the other question, what is the standard deviation? So B, standard deviation, sigma square is the variance. Variance is equal to B minus A square over 12. So that is going to be 10 minus 0 square over 12. That is 100 over 12. And therefore, the standard deviation is going to be the square root of 100 over 12. So 10 divided by square root of 12. You'll get an answer. What is the answer for this? 2.886. Okay, so I'll take it as is. So the answer is 2.886. Correct. Okay. Right. So I think that's very straightforward. You can understand that without any trouble. So this is how a uniform distribution would look like, and nothing much to discuss. Right. Now the second topic, you can do the other questions. You have other questions like some. Okay. If you want, I can do another question so that get some idea better to do it. Okay, the scheduled commuting time on the Long Island Railroad from Gleecock to New York. Right, let's do this question as well so that you can get an idea about the things. Right. Right. The scheduled commuting time on the Long Island Railroad from Glencoe to New York City is 65 minutes. Suppose that the actual commuting time is uniformly distributed between 64 and 74 minutes. Right. The first thing, as I told you, take it and draw it. So suppose that the actual commuting time is uniformly distributed between 64 and 74 minutes. So when you realize that it's uniformly distributed between these two times, it means that you have an equal probability of observing a time that is between 64 and 74. So in our case, or in this scheduled commuting time of the Long Island Railroad from this one is 65 minutes, right? Suppose that the actual commuting time is uniformly distributed between these two values. So our A is 64, our B is 74. What is the probability that the commuting time will be less than 70 minutes. So less than 70 minutes. First thing, find out what is this fx. So fx is 1 over b minus a. So that is going to be 74 minus 64. That is 10. So fx is again 10. That's easy to remember. So this is 1 over 10. Fx is 1 over 10. If you multiply this one, you get the total probability of 1. So the question asks us, what is the probability that the x is less than 70 minutes? So p, x is less than 70 minutes. So that is going to be this whole area. X and 70 minute means basically the function itself defines as anything here is 0, anything here is 0 as well. So in order to find something like this, because this is it's kind of a step function, you have to define it like this, where you have the probability of that random variable being less than 64 plus the probability of that value being in between 64 and less than 70. Why is that? Because this particular uniform function, uniform distribution exists between 64 and 74, and below the 64, the probability is 0. But you have to mention that such a thing exists. So px less than 64 is going to be 0, plus this is obviously going to be the area between under this range. So 64 to 70, you have 6 times 1 over 6, 1 over 10. So that's going to be 0.6. That's 0.6. Between 65 and 70 minutes, between 65 and 70 minutes, right? So between 65 and 70 minutes, I don't even need to write it. So this is 5. 5 times 1 over 10, that's going to be 0.5. And greater than 65 minutes again. So when you think about the probability of x being greater than 65 minutes, you have to be very careful, because our upper bound for the uniform distribution is 70. So the probability of x being greater than 65 less than 70 plus the probability of x being greater than 70, or we can following the same notation, you can write 7 greater than 70. Right. So in that case, this is 0. 65 to 70, that is 5 again. So that's going to be 0.5. What are the mean and standard deviation of the commuting time? So mean and standard deviation, mu is a plus b over 2. So it should be 74. Right. Yes, sorry. I didn't see that. 74. Sorry, 74. I was thinking about the previous question. Sorry about 74. 74. So 65 to 74. That's 9. Right. So 0.9. Thank you. I was in this one. I can't see the previous one. So yes, greater than 65 means 74. Yes. So 74 above is 0. 70 up to 74 you have. Yeah, but for the other ones, yeah, 70 is correct, right? Thank you. And mu is a plus b, and you have a plus b here. So 64 plus 74, 64 plus 74 divided by 2. So that's going to be 69, right? 64 plus 74 means you take 60. So you have 10, that is divided by 5, that's 2. So that's 69. And sigma square is going to be the square of b minus a divided by 12. So b minus a is 10. 10 square again, 100 divided by 12. So sigma is going to be again the same answer, 8 point something, right? 2.866. Right. Right. So that's how you do it, and I think others can also find out something more about these questions, and in the tutorials I think you learn more. And now please help each other. So you are working as a group, nobody is working alone. You can help each other when you are working as a group. Don't ask them to copy your answers, but help them. If somebody doesn't understand something, you can, if particularly because of the language barriers, or some sort of technical problems, or problems finding difficult for accessing internet, etc., help each other so that they can, learn from you. So that's the whole idea of grouping you together, so you can work as a group. Right now, we'll go to the exponential distributions. So when we buying a scientific calculator, what type of model calculator is better for us? I think you are in your um, uh, is it what do you call it? Orientation. In the orientation, didn't they tell you what sort of a calculator you should buy? Like when back 10 years ago, we used FX991ES. So FX991ES was the standard model for University of Moratuwa back in the day for engineering. So Faculty of Engineering used FX991ES. I think now it has a new model. If you search that, you will find the calculator. So let me, if you want to see that, like this FS991ES. I think this plus calculator is what I think came afterwards. This is the calculator. FX991ES plus. This is approved by the university. This calculator. It's called FX991ES plus. So we used to have FX991ES. Where is that? This calculator. This is the calculator that I used 10 years ago. So ES plus is the one that I saw most of your, I think the engineering students, they use this. I think FX 991 ES plus is the one that is approved. Right? I think that's clear. Okay, so let's go to the exponential distributions. Right. The exponential distribution. What do you mean by an exponential distribution? Right. So I'll give you some example about an exponential distribution. So an exponential distribution is something like it's, if you how many of you have done like can I know, um, is there anybody who comes from A-level mathematics background? Are all of you coming from the commerce and other related streams, rather than you don't know anything about physics, right? One answer is enough. Like if you all come from commerce backgrounds, you can just say yes. I think nobody is coming from a physics background, right? I think, right? I think all of you come from commerce and related backgrounds, right? Not from physics, right? Most of our coming from commerce background, right? Now, when we, I can give you an example related to commerce as well, but the easiest thing to remember is from something that uh, let me find a good example so that you understand what is this exponential thing is. Right. So the word exponential means that it actually increases or decreases as a power. So if you think about um, uh, let's say there are a few mathematics students as well. Okay, that's good to know. Right. So those who are coming from mathematics background, they know what is exponential distributions already. So exponential means you have a value and it's kind of cutting it half and half and half and half kind of. So it's not the exponential distribution that we discuss here, but it's a good starting point. Imagine that you have a ribbon. Let's go back to our ribbon example. So you have a ribbon, right? So this is your ribbon. And you take this ribbon and your friend asks you to follow this little game. So the game is you have to cut this ribbon like 2/3 of the ribbon every time. You, let's say you have this ribbon, so this ribbon say 3 centimeters, so this is 3 centimeter ribbon. This is a 3 centimeter ribbon. So your friend asks you to cut it 1/3 every one. You cut 1/3 out of it every time. So you take it, and then this is this is the first time that you, this is the first instance, and you take the ribbon. So this is your ribbon, and what you do is you cut 1/3 of it. Sorry, now 1/3 of it. Cut and remove the 1/3 of it. So you are left with 2/3 of it, right? So now you are here 2 centimeters. So this is the second instance. Right, then your friend take it from you, and what she does is she cuts 1/3 again from this one. So you may left with something like this. So now 2 minus 2/3. So it's like some value, we don't need to worry about it. So likewise, you keep on cutting this in that way. Right. Now, if you keep these things in order like that, and then try to draw a curve that matches all these edges, you will find something like this, right? Actually, this is an exponential growth or a decay. We call this an exponential decay. So if you convert this whole thing and rotate the whole thing other way around, like pillars, you will find that it starts from some value and then it just keeps on decreasing, right? Like that. It decreases. So the idea behind an exponential distribution is that you have a starting value and it keeps on decreasing, and the decrease itself is a function of the previous value. So you have some value here, and this value get reduced by a certain number when you multiply it, and again and again and again you just kind of reduce that value. So that's the nature of exponential distributions. So if you think about our foreign reserves, Sri Lankan foreign reserves, you have say 200 million US dollars, and then somebody invest on something, say $100 million. So 200 minus $100 million. Now we have, previously we had $200 million. Now we have $100 million, and then somebody else comes and invest $70 million from that. So $200 million, $100 million, and now we are left with $30 million. So likewise, you have to have a previous thing, and your expenditure or your reduction depends on that previous value, but it can never be equal to the previous value. So it can be a exponential decay or an exponential growth. So if you understand the nature of how this happens, it's easy to understand the equation. So the money in your pocket is also a good example of exponential function when you start spending. So say your parents give you 10,000 rupees when you come to the university. They give you 10,000 rupees, and you have to spend that 10,000 rupees, right? You have to spend on eating, traveling, and also maybe boarding fees, and for books, and also other needs. So you have to spend that. So the initial money is there, 10,000 rupees, and for each of the expenditure that you incur, there is a reduction from that money. So on the other hand, the same thing, if you invest something, you invest 10,000 rupees on something, and you will get dividends and other things, and you keep on accumulating things on the previous value. So something of that nature is an exponential distribution, exponential growth or a decay. The function for the exponential distribution, fx, the function for the random variable of this exponential distribution is called lambda e to the power minus lambda x for all x's greater than 0, which means the value should be a positive value. So in the case of mathematics and other physics and other stuff, negative values can be something to consider, but in terms of money and other things, as long as you are considering about the positive entities, it's okay to, you can think about positive values, but the function itself is defined for the positive values. So positive values, greater than 0 values, not the negative values, negative 1, negative 2, no, it's all positive values, right? So what is this lambda? This lambda is that that mean thing that you are going to get, that is the body of this sun, right? So it's like that. So I told you that your parents gave you 10,000 rupees, but it not be the case all the time, right? It is not the case. Sometimes you might get 15,000 rupees, sometimes you get 8,000 rupees, sometimes you get 5,000 rupees. So likewise, it can be a fun, it can vary, but as an average, if you take if you think about 12 months starting from January to December, if your parents for every visit to the university, or when you leave the house, you receive, when you leave home, you receive equal amount, something like 12,000, 8,000, 5,000, 6,000, different values. Then when we add them together and get the average, maybe that is 10,000. So when you add up all these things and get the average, maybe that is 10,000. So that lambda here is this mean value. So the value that you received as a macro, as a macro number. So it is called the mean number of this distribution. Lambda is that mean number of the distribution, right? So if you think about that, and then x is any value of the continuous variable where between 0 and infinity. So x can be that value, maybe the amount of the time that you spend on it, like the number of times you spend something, that defines your expenditure or your income, or as I told you, the number of cuts that you make, likewise. So x is that value, right? So we are talking about continuous distributions. Therefore x can be any value between 0 to infinity, which means you can have 0.1, 0.2, 0.3, 0.1, something, any decimal value also is a possibility. So lambda is a fixed value, that's a constant value, and e is also a value, although e is here uh, is a is a letter, it's an algebraic letter. But if you remember the normal distribution, that same e is here. So e is equal to 2.71828. So that's a number. You remember this from the normal distribution. Normal distributions, if you remember, the function is 1 over square root 2 phi sigma, and then you had this exponential function negative half x minus mu divided by sigma square, remember? So this e is this e, the same e. So it's a natural logarithm. It's called the mathematical constant for the natural logarithmic. So that's 2.71828. It goes on. And lambda is the mean, and we can say mean number of whatever the things, mean values, or the mean number per unit, and then x is the value that of the continuous variable. X is the continuous variable, and x can go up to infinity, right? So that's the idea of the exponential distribution, right? So the things to remember again, things to remember: the mean is equal to 1 over lambda, and the standard deviation is equal to again 1 over lambda. So if you consider about an exponential distribution, you have mu and sigma both have been 1 over lambda. And the other thing to remember is that the cumulative exponential probability, like the probability, cumulative probability, cumulative exponential probability, that is the probability of something being less than a given value. So this is simple x, that is capital X, being less than or equal to something that is equal to 1 minus e to the power lambda e minus e to the power minus lambda x. So this is how you find the probability. Okay, so this is the function fx, this is the probability function, this is how you find the cumulative probability of something. Remember how we did the probability calculation for the normal distribution looking at the table, but here we don't look at the table, we can directly put this e to the power something here for the values. And if you want to get the probability density function, it goes like lambda e to the power minus lambda x. So you integrate it and then you get it. Those who are, who like to do the math and find out how this comes, you can integrate this one between some value to the other, and you'll get this answer 1 minus e to the power minus lambda x. So this comes basically, so this comes from when you do px less than or equal to capital X, that is equal to negative infinity 0, sorry, 0 to x, lambda e to the power minus lambda x dx. So when you do this calculation, you'll get this thing. Right. So let's look at a question if we can. Continuous. All right. There is an example here. The exponential distribution is a continuous distribution that is right skewed and range. So right skewed, if you remember what is skewed, if you have a tail towards your right side, that is right skewed, ranges from 0 to positive infinity. The exponential distribution is widely used in waiting line. So waiting line means because you have time and it just queuing on, like if you think about the petrol queues, right? So you have a very long petrol queue, and with time it just kind of reduces and goes to 0. So theory to model the length of time between arrivals in processes such as customers arriving at a bank's ATM, patients entering a hospital emergency room, hits on a website, etc. The exponential distribution is defined by a single parameter. Remember this one. Please remember this single parameter is very important. I'll put it in the note as well, because when you learn about parametric things, you will need this. The exponential distribution is defined by a single parameter lambda. So the chat, sir, can you explain cumulative exponential? I missed that part because of work connection. Okay, so cumulative probability means this thing. So you should be aware of it by now. Cumulative probability means if you add the probabilities, you add them up in the case of a discrete probability distribution. If you have something like the probability of xi equals 5, plus the probability of xi equals 6, kind of, you add these probabilities together. So we call it cumulative, the addition of probabilities. So in the case of continuous probability distributions, you have a function. So if you remember the normal distributions, what we call cumulative probability means the probability between two ranges, right? Two values. Now, in the case of exponential probability, you have this exponential function like that. Then it goes decaying function. So the cumulative means you have you think about a probability where you fix this one in a range. So here the probability of x being less than a given value. So this is simple x, that is capital X. So if you consider the capital X here, p x less than x means the probability of that value being less than the capital X. So that is taken as an integration of this function. This is then the density function of this equation is of this exponential distribution is lambda e to the power minus lambda x. If you look at your density function, then by the from the basic principles, how do you get it? You have to get this from all the way from the lower bound all the way up to the upper bounds of the limiting function. So that goes as an integration from 0 to x, lambda e to the power minus lambda x dx. It goes like that. So when you do that, you get 1 minus e to the power lambda x. So if you, for example, if you are asked to get the probability of say something something like this, say say what is the probability that x is less than 3, right? If you get something like this, so you can, without doing this integration, you can find this 1 minus lambda times 3. So you get a value for lambda as well. So you just need to substitute that, and then you get the answer minus say lambda equals 5, then 5 times 3. So you'll get the answer for x being less than 3. So that's the idea. Okay, so that's the idea of cumulative exponential probability. Right, what I was telling is the exponential distribution is defined by a single parameter lambda. That's because lambda is there and x is the x here is the random variable, that value that you put in, and lambda is that the parameter for the distribution, like the money that your parents give or the investment or etc., the initial thing. The mean number of arrivals per unit time, the probability density function for the length of the time between arrivals is given by this equation. So that is it. The mean time between arrivals is 1 over lambda. So sigma is 1 over lambda, and then cumulative exponential probability is 1 minus e to the power minus lambda x. So let's look at this example. To illustrate the exponential distribution, suppose that customers arrive at a bank ATM at a rate of 20 per hour. Now that's a good thing to start with. Let me start there. Now here you can look at this thing. This is the cumulative probability, cumulative exponential probability. So this is arrival time being less than or equal to 0.1. So if you remember, the equation should go as 1 minus e to the power minus lambda x. So this lambda, if you take a look at this lambda can have a unit. So this lambda should have a unit because x is a time. Okay, please pay very close attention to this. So x is a time. So if what is the probability that the next customer will arrive in within 6 minutes? So x is a time. X is a time. So imagine that this lambda doesn't have a unit. Okay, so if lambda doesn't have a unit, if it is just a number, then number times a time will give units to this power, e to the power some unit, which is not going to be executable. You can't actually get a value. When you, if you have a power, the power should not have a unit, right? It should not have a unit unless it is a what we call an empirical equation. For theoretical equations, the power should not have a unit because it's just a power. So in this case, lambda, I'm telling you an easy way to remember. If you forget what is lambda, the lambda comes as a rate. So rate means for a given time. So here it says the rate ATM at a rate of 20 per hour. Okay, so it says 20 per hour, which means lambda is not just 20. Okay, it's not that 20. Lambda is 20 per hour. Remember that. Lambda here is 20 per hour. And the question says 6 minutes. Within 6 minutes, which means 6 minutes means 6 divided by 60, which is 0.1 hour. Okay, so when you multiply this lambda times x, what it does is this unit cancels out. So hour to hour cancels out. That's what happens here, right? So if you again, if you want to recollect what I said, you have a lambda. Lambda is a rate or an average. As I told you, I gave you an example like the money that you receive from from home. So you have the values all along the year, and then it's like per month, right? Per day or per hour, per minute. So every time lambda has this rate. So the value, the random variable is a time or a distance or something like that. So for example, if somebody says in a given road, you have two signal stations, or you have say two bus holes, right? Two bus holes per kilometer. So 2 bus holes per kilometer. Lambda is 2 bus holes per kilometer. And how many bus holes will you find in the span of 5 kilometers? So if you are given these information, lambda is 2 bus holes per kilometer, and how many bus holes are you going to find within 5 kilometers, then the number of bus holes you can calculate the estimated from 1 e to the power minus lambda x. So in this case, lambda is 2 per kilometer and x is 5 kilometer. So these cancels out, and then you can get a value for a less than 5 kilometer, how many bus holes you are going to encounter. So similarly, every time, remember this, lambda has a unit and that unit is going to cancel out with x unit. So if you understand this one, it is easy, because lambda is actually an average or a rate, the rate of something, an average of something. So that unit is going to cancel out with the unit of x. So um, other than that, these are just arithmetic operations. It's very simple. The probability that a customer, you just do the math, and you can get it. So if you have the scientific calculator, you can put exp here to get the e to the power something. Or if you have your Android phone, or your, I think your mobile phone, Apple or Android, whatever, so you can get this app. There is an app for scientific calculators. You can get that and do the same thing. So until you find a calculator. So that's easy to estimate, right? So let's do a little example here. uh, we'll start with a very simple one. Given an exponential distribution with lambda equals 10, what is the probability that the arrival time is less than x equal less than x less than zero point 0.1, greater than zero point 0.1, between we'll start with this simple example, and we'll go to the harder ones. Right, so it says yeah, here the problem is you can't really um, uh, you can't include those lambda, so I'll just say lambda. The can example, I think I can. Simple. I can copy this directly. Yes, lambda. Right. So given an exponential distribution with lambda equals 10, what is the probability that the arrival time is less than x equals, so I'm not really happy about this notation. It should be less than 0.1. Why should you say less than x equals something? Very stupid. Right, so you have lambda equals is 1. So if you follow my instructions, best thing is to just draw something like this. So if you have an exponential distribution, so you know that fx should be lambda e to the power minus lambda x. So in the case of this question, it says lambda is 10 to the power minus 10x, or something like this. It goes like this. So what is the probability? A less than x equals, so that is the probability of x less than 0.1, less than or equal to 0.1. So that goes like 1. So this is the function. Remember, this is the function. Cumulative function is px less than x, that is equal to 1 minus e to the power lambda x. So that is the cumulative function. So you have to apply the cumulative probability function to get the probability between ranges 1 minus e to the power minus lambda 10 x 0.1. So 1 minus e to the power minus 1. So you can find the answer here for b greater than, so px greater than 0.1. So, all right, here that's a good example. So how do we find x greater than 0.1? So x greater than 0.1 is basically, if you have x here, x somewhere here, this function px less than or equal to something, this is for x to the left side, right? So Px greater than 0.1 means this range, this particular range. So in order to find that one, what you can do is, this is actually from the probability, the theory of probability, we know that the sum of all these things, the total probability should be 1. Therefore, anything x greater than 0.1 should be equal to 1 minus the probability of x mean less than 0.1. I'm not going to put equal here because we have to find probability x equal to 0.1 as well. So to avoid that one, I just put x less than 0.1. So 1 minus px x less than 0.1 is the same probability that you find here. So that is 1 minus e to the power minus 1. So I end up with getting the probability e to the power minus 1. So if you get this value, so that is the probability of this. Okay. Right, between x.1 and x.2. So between, right, let's go to the question number C. Probability of x between 0.1 and 0.2. So 0.1 and 0.2, is it equal sign? Yeah, 0.1 and 0.2. So this is the question. So in order to find this one, what should we do? Remember your lessons with the normal distributions. If you have a range, always try to draw this 0.1 greater than 0.1 less than 0.2. So what we need to find is greater than 0.1 and less than 0.2. So this is the region, the region that we need to find. So what do we do? If you remember your normal distribution calculations, what should we do? This range is also equivalent to px less than 0.2, right? Minus, because this is that range, less than 0.2 minus p less than 0.1, because then only you will get this range, right? So that is going to be equal to px less than or equal to 0.1. That is going to be 1 minus e to the power minus lambda. Lambda is 10, x is 0.2, right? Minus 1 minus e to the power lambda 0.2, that's 0.1. So when you do the math, 1 to 1 cancels out, this becomes positive. So the final probability is going to be e to the power minus 0.2 times 10 is, that's going to be 2, that is minus, right? So this is going to be positive, that's 1, e to the power minus 1 minus e to the power minus 2. This is the answer. So this is not the answer, you have to calculate, get the calculated answer, right? I'm just doing it quickly. Right, so that's about it. Less than is 0.1 or greater than points. Right, so the last one, probability x is less than 0.1 and O p is greater than 0.2. So this is what it asks. Right, in this case, draw your thing again. Take this exponential distribution. P is P is less than 0.1. Draw your 0.1, less than 0.1, greater than 0.2. Put your 0.2 here, greater than 0.2. You need to find this, but you already know this. You already know this. So what can you do? This is very simple. The whole area under the curve is 1 to the, how to say, one way of answering this one is one way. Okay, one type 1. So one way of answering this one is simply 1 minus the previous probability, because the whole area is 1 and you just get rid of this area, then you get the area under this curve. The second type, the other way of answering this one is type 2. Answering this one is, look at this curve again. You need to find the area here and here. right? So that's the area you need to find. So simply what you can do is you can find this one without much effort, x less than 0.1. It's very simple. To find this part, what you need to do is you need to get 1 minus. So to get this part, you need to find 1 minus probability x less than 0.2. So this is that block. So add them together, you will get the probability, right? So either way, you'll get the same answer. Okay, so that's how you do that question, less than or greater than 2. So you can, that's a very simple question. So let's go and look at the other questions we find here. Something that is kind of fair, some harder questions here. Final one. We'll take this one. Question says some internet companies sell a service that will boost websites traffic by delivering additional unique visitors. Assume that one such company claims it can deliver 1,000 visitors a day. If this amount of website traffic is experienced, then the time between visitors has a mean of 1.44 minutes per minute. So look at this, has a mean of this much or 0.6944 minute per minute. This has a mean of this one or per given a minute you have this much. Assume that your website gets 10,000 visitors a day and that the time between visitors has an exponential distribution. What is the probability that the time between two visitors is less than 1 minute? So this is a very good question. Now it says it can deliver 1,000 visitors a day. If this amount of website traffic is experienced, then the time between, so if you find 1,000 visitors, the time between visitors as a mean is this much. So per given per minute, right? Per minute, you have this much, 0.6944 per minute. So less than 10 minutes, less than 1 minute, you have to get this multiplied by this to get the e to the power lambda x, right? So because you have per minute, remember the units I told you, per minute. So if you don't know the units, you can go back to the calculations. If you remember your mu is actually 1 over lambda, right? Your mu is 1 over lambda. If you remember your math, your mu is 1 over lambda. Then you can actually check if your mean is 1.44, right? If your mean is 1.44, then you can check 1 over 1.44. What is the value? 1 divided by 1.44 is going to be 0.6944. Did you understand what I say? It says a mean of this much. So mean, this is the question. If you did not receive this one, okay, how do you get the lambda? This is not lambda. Mean is this much. Lambda is not given. How do you get the lambda? You know that mu is 1 over lambda. Remember? So if mu is 1 over lambda, if your mu is given, mean of 1.44 minutes. So if your mu is given, then you need to find lambda. Lambda is 1 over mu. It's 1.44. So you'll get 0.6944. If this is not given, okay, I'm saying if this is not given. So if it is given as given here, then no issues. But when it is not given, you have to convert mu to lambda and lambda to mu depending on the context. Assume that your website gets 1,000 visitors, and all of a sudden, if you are asked to calculate the mu as well, then you have to go step by step and get the mu and lambda and so on and so forth. Less than 1 minute, less than 2 minutes, more than 3 minutes. The time between visitors has an exponential distribution. So do you think it is reasonable to assume that the time between visitors has an exponential distribution? So it is if that's the case, you have to prove this the exponential part of it, like uh, just draw it and show whether this goes like that, and lambda e to the power minus lambda x curve is fit. So you can look at the distribution and either draw it or look at the probability, the properties of the distribution, and say how it behaves between each values. So you can argue on that, right? So I think we'll learn more about the exponential distributions as we and the other distributions as we do other calculations about these things in the tutorials. And there is a simple thing that rather something that I would like to discuss about the normal approximation of distributions, which we stopped here. What is this normal approximation of distributions? So evaluating normality. In order to do this, I want to visualize the distributions. So when we visualize the normal distributions, when we have this, we have proper like um, we have a means of getting this one. I'll keep this one for maybe somewhere in the future to discuss, maybe through a tutorial or something, because this requires some sort of a drawing. So drawing in the sense sketching out the probability. So I'll find some time to do this one here, or I'll put a question somewhere here and there, so that will be covered in the. And the next topic that we'll be discussing here is sampling and sampling distributions. So before I get into this particular thing, probability samples, and about the sampling itself, I want to tell you something before we stop the lecture today. I'll discuss this one on a next lecture, on a separate lecture. So please have this in mind. Now, when you start statistics, I think I may have done this one previously as well, but anyways, I'll tell you this concept again. When we discuss about statistics, we have something called inferential statistics, inferential stat, and descriptive statistics. Descriptive statistics. So descriptive statistics is the thing that we actually can grasp, which means when we think about a sample, you can think about the mean, the standard deviation, the variance, maybe the mid value, the max mean. All these things you can identify in a descriptive statistic. So a descriptive statistic is itself a description about the sample. So this belongs to sample. Anything that you take, the sample that you have with you, maybe your customer log, maybe your daily sales, maybe your daily revenue, the income that you have per day. So all these things, the sample that you have, sample that you can have your hands on. So that is descriptive statistics. Anything that describes the sample belongs to this descriptive statistics. But inferential statistics means this inferential part is actually it's about the population. So it's about the population. Now, what is population? Now, if you have a business, say that you are selling candies, you are selling chocolate. So you have a chocolate business, you are selling chocolate. Now, your business is not the only one, right? There are other businesses as well who sell chocolate. So others sell maybe chocolate toffees, you sell chocolate bars, maybe ice cream, all these chocolate related. Somebody else is also selling chocolate related other stuff. So the population means that all these things, like you are just a part of it. In the population, you will find all the sorts of chocolate vendors, different types of chocolate sellers. All these people, their accounts, their business relations, their logs, everything will be in that population. So you are just a sample of it. You will find so many other related businesses having related accounts, same samples, same similar numbers elsewhere. So that's the population, right? So from sample to the population, we do this inferential statistics. Now, from the population, picking a sample, this depends on the probability. You have a probability of picking a certain sample. So if you are in the chocolate business, you have different types of chocolates. You have chocolate bars, you have chocolate toffees, all these things. Let's say that you specifically want to check whether a certain toffee, certain chocolate toffee, has the weight. So you have, let's say, 1,000 toffees in your store, and you can pick 5 toffees and then do check the weight of those chocolate toffees, and maybe you'll find say 5 grams each, or 5.5, 4.8. This is how you get it. So there is a probability of picking a certain weighted chocolate. So this probability of picking a candy, a chocolate bar, or a chocolate of a given weight, right? So this is the probability of sampling. You pick something from the population, and that is the probability. So you have a probability of picking the sample from the population, and you use descriptive statistics to describe about the sample. If you take 5 topics, you have the average of the weights of those 5 topics. So that's a descriptive statistic. And then you talk about the population from the sample. This part is inferential statistics. So this is where we talk about sampling, we talk about confidence, we talk about hypothesis testing, we talk about many things, because we use the sample to infer about the population, the large set. So we call it the superset. Talk about the descriptive statistics. We use the descriptive statistics to describe the entire population, not just the sample. So that is inferential statistics. So the bridge between the inferential statistics and descriptive statistics, this comes from the sampling probability and how we pick up samples from there. So the sampling distributions, and we call central limit theorem, and all these things comes from this entire picture of things. So have this in your mind. There's a probability of picking something from a population, and there's a description for the sample, that's descriptive statistics, and from there we infer about the population, that's inferential statistics. So keep this entire picture in your mind, because in the next lecture we'll be talking about the sampling distributions and how to sample, and also about how the sampling variations occur, and etc. about things to consider. This is an important lecture. All right. So for today, I can stop here. So right. So good luck for the next one. Let's meet. Please attend the tutorial tomorrow, and hope to meet you next week.